Enzyme inclusion in animal diets is commonplace due to the numerous nutritional and zootechnical performance benefits they deliver. In this Huvepharma focus, the factors affecting enzyme recovery, especially during the pelleting process, are considered. Professor Mia Eeckhout is a full professor in the Department of Food Technology, Safety and Health at Ghent University, Belgium. Her work focuses on the effects of new feed ingredients on the technological processes used to manufacture compound feed.
Hello, I'm Professor Mia Eeckhout from Ghent University, and I welcome you on the presentation of the pelleting process and the recovery of enzymes. Now, enzymes are commonly used in animal feed. Feed enzymes can have a lot of advantages as they increase the digestibility of the nutrients, they have a positive impact on animal performance, and they can reduce environmental impact of livestock. So we may expect that the coming years or decade, the global enzyme market will even increase. The mode of action of enzymes can be described by the lock and key principle. The enzyme can bind a substrate and breaks it apart. But important to know is that an enzyme is a protein. It's an active protein. And the protein can be denatured due to temperature. And due to this fact, it loses its activity. So it's obvious that this is the drive for the research for more heat-stable enzymes. One of the key steps in feed production is the pelleting process. After dosing, milling and mixing, the mash is conditioned, pelletized and cooled to form granulates or pellets. Before pelleting, the feed mash is conditioned. It's an important step for the physical quality of the pellet. The conditioner is a cylindrical vessel, and the cold mash comes in at a temperature below 35 degrees Celsius and a moisture content lower than 12%. And we will inject steam at a temperature of approximately 130 degrees Celsius at a pressure of 2 bar. After this, the feed mash leaves the conditioner at a temperature which may rise up to 90 degrees Celsius and the moisture content up to 15 or 16%. In the next step, the conditioned mash goes to the pelletizer. The pelletizer is equipped with a die, and the transfer of the mash through the die generates friction heat, which increases the temperature of the pellets. Die holes may differ in length and also in diameter, which will give different friction. The higher the L over D ratio, the higher the compression and friction, and the higher the heat impact. And then the last step in the process is the cooling step. The cooling takes place in a countercurrent cooler. It's a cooler where the pellets come in warm and moist at the top, and the air, which is ambient air, which is used to cool and dry the pellets, comes in at the bottom. The aim of the cooler is to reach a final temperature which is around ambient temperature and a moisture content which is below 14%. It's quite very important because inadequate cooling will reduce shelf life and have a negative impact on pellet quality. So now knowing the pelleting process in detail and a little bit more about the properties of the enzyme, we can dive deeper into factors involved in recovery. And the first factor is the conditioning temperature, but also the conditioning time. From practice, we know that if conditioning temperature increases up to 85, 90 degrees and even more, there is a huge impact on the recovery. It decreases. But if the conditioning temperature takes 30 seconds up to 2 or 4 minutes, we know that the impact is even worse. So temperature and time reduce enzyme recovery. The equipment used in the process is also important. We have a lot of different conditioner types. We can talk about short-term or conventional conditioner mixer. We can talk about long-term, a hygienizer up to 2 or 4 minutes of conditioning, and a high-pressure conditioning, for example, the expander. And then we can talk about steam quality. In the process, we should use dry steam, and dry steam is steam where we do not have any condensed water droplets. We should reduce them so that we don't have an excess of water added in the conditioner. And the third parameter is the dye features. The dye feature, meaning the L/D ratio, can differ in practice between 10 to 20. The higher the L/D, the higher the friction heat, and the higher the impact on recovery of enzymes. Feed composition is the other parameter which is important. It's also friction related. This means that all ingredients or nutrients which increase friction have a negative impact on enzyme recovery. This is the fact for fiber and minerals. They increase friction, and so we find lower recovery. On the contrary, fat is a lubricant. So fat will decrease friction and friction heat, and the recovery will be higher. So in this slide you see that for fat content up to 3%, even at conditioning times of 85 degrees Celsius, we still have a higher recovery than, for example, in feed mixtures without fat. Protein and starch are of less importance. The cooling step is the last step in the production process. We make the difference between slow and fast cooling. Slow cooling is inadequate cooling, so it will also have a negative impact on enzyme recovery. If you would like to perform some recovery experiments in your own facility, we would like you to give some advice on best practices. You have to take care about your sampling procedure. We advise you to take multiple samples, between 5 to 10 and of at least 500 grams. Take those samples over the complete batch, excluding the start and the end. Take mesh samples at the conditioner inlet and take pellet samples, preferably at the cooler outlet. You can also take them at a dye outlet, but then keep in mind that you have to cool them very fast. And then if you want to go for analyzing, you can take all samples to the lab. But you also can pool the samples and take, for example, 3 pooled samples to analyze enzyme recovery of your production process. And then the last step is the calculation of the recovery. In fact, we should correct for background activity of our enzymes, as we know that also our feed ingredients have some enzyme activity. The correct calculation is to take into account the activity in the blank pellet as well as in the blank mesh. But we know that, however, in practice, this is not possible, because in the real feed mill situation, you do not have a blank feed. Therefore, you only can calculate the simple way, making the ratio of the recovery in the pellet to the recovery in the mesh. To illustrate this, let me show you this example. In this table, we calculated the enzyme recovery, first taking into account the blank background enzyme activity, and secondly, without taking into account the activity of the blank. And the results are clear. If you take into account the blank background recovery, the results are higher than if you don't. So let us make some conclusion on the parameters affecting enzyme recovery. First of all, we had the conditioning temperature. The higher the temperature, the lower the recovery. Then we have the conditioning time, long versus short conditioning. The dye features, as we saw, that a high L/D ratio will also have a negative impact on enzyme recovery. Inadequate cooling will also reduce the enzyme activity after pelleting. And feed composition is another important factor, as we now know that the higher the fat level, the better the recovery. The higher minerals and fiber, the higher the friction and the lower the recovery. And don't forget, sampling procedure is crucial. So thank you for your attention. I hope you enjoyed this presentation.